everyone. We are going to have as a presenter today Paula González. She's a master's student at the Observatorio Astronómico Nacional and Universidad Nacional de Colombia. And currently she's on exchange at University of Graz in Austria. And she has a bachelor's degree in physics, where she right now she's investigating the solar flare precursors and the statistical validation of the flare anticipation index, FAI, using GOES soft X-ray observation, which is the topic, today's topic. So please, Paula, welcome to CRAAM, Mackenzie, and you can share your screen and start. The stage is yours.
Okay, thank you very much. I'm going to share my screen, and please let me know if you can see the presentation, the slides.
Yes.
Good, good. I'm going to turn off my video because my computer and my internet is slow. Well, as we can.
I think if you're trying to drag this button, I think you can click it anywhere and just drag it.
Where can I hide?
Yeah, there's a way to hide. I don't remember how. There you
go. Okay. So my name is Paula González. I'm doing a master in astronomy, as you said, in Colombia. But now I am here in Austria, in the city of Graz, doing an exchange in order to finish my thesis. So this is the name of my thesis. I'm trying to study how to predict solar flares. So first, thanks to Fabiana and Eduardo for inviting me to this seminar. I really appreciate the opportunity to be here today. Okay, so what exactly is a solar flare? Solar flares are sudden and intense releases of magnetic energy in the solar corona, often associated with active regions and magnetic recognition processes. Here we can see these images that we have through SDO and AII. And we can see these different views of solar flares through different wavelengths. So why it's important to predict or anticipate these solar flares is because the impact in our technology, because they can damage satellites and disrupt communications and GPS. So it's important to predict because until now we don't know how and when will be a solar flare in the solar disk. And we don't understand very well how the sun produces these events. Right now, we have several ways to predict solar flares, but these methods have some problems, and we want to explore a different approach, looking at thermal signs before flares, which is what my research focuses. We can see in this plot of SOC asteroid data from GOES, the sensor X-ray S. these phases of the flare. And in this graph that I take from Hudson, shows exactly what we can see just before the peak of the flare. It's like a slow rise just before that Hugh calls hope. So we want to explore and study this hope, that is the Hot Onset Precursor Event. Hugh proposed this index, flare anticipation index, in his recently work from this year. And he explores only 20 flares in this paper. So we want to extend this statistical study. My general objective is basically test how well the FAI index actually works for predicting solar flares using GOES satellite data and looking at the physics behind it. So we want to analyze the historical data to find these FAI signals just before a flare and do a statistical validate if the FAI can predict flare in all flares or all the classes of the flare. And we want to understand the physical mechanisms behind the precursor signals. So we want to see here in the phases of the solar flare, and we see here that in this soft X-ray data, we can see this increase in the pre-flare phase. So we want to study just this phase. Well, let's talk about the physical behind the solar flares. The main energy release comes from magnetic reconnection, which accelerates particles and hits the plasma, creating emission across all wavelengths. But the interesting for our work is what happens before the main explosion. We want to see the gradual heating in this soft X-ray precursor that Hughes calls Hot Onset Precursor Event. We can see in this plot this horizontal branch that shows the hope when the temperature is almost the same, but the emission measure increase just before the sudden release of the flare. So we want to explore these two aspects, temperature and emission measure. And how we actually measure these parameters, we use GOES satellite data from two X-ray channels, the short channel and long channel. And from these fluxes, we calculate the temperature and emission measure using a function of some pi. If we can see this horizontal branch, this hope in all the flares, that means that we can predict that the flare will be in the solar disk. So Hugh defined this like a gradual increase in temperature and emission measure before the impulsive phase, and he defined his index with these parameters. Here we can see in this plot these red vertical lines. That means that this pi is triggered, this alert is triggered, and is saying that in the future, near future, will be a solar flare. he used these parameters after calculating temperature and emission measure. He says if the emission measure is greater than 0.005 and the temperature is between 7 to 14 million of Kelvin, there is a trigger of this FAI. That means that in the near future there will be a solar flare. And he wants also to explore in the future the FAI duration. It means that if this trigger remains after some minutes. So we want to explore this in the near future too. Some key concepts. GOES give us temperature and emission measure data that we can calculate, and we want to understand the data of the GOES. So for our analysis, we use data for all the GOES satellite series. This time, line shows the different GOES satellites over the years. As Hugh only studied a few FLARES in 2024, we want to expand the statistics for all over the years in this era of the GOES satellite. So we will use the data of the XRS instrument that give us this soft X-ray data. And we want to explore all the solar cycle between 1980 until now. We want to explore almost 4-5 solar cycles. For a coverage of more or less 45 years, and we want to use data with a resolution of 1 minute, and we need to correct the background values, and we use the same method that Hugh used. So now we are doing the statistics with 1,000 of days that we selected almost randomly between these 2 years with a same interval between days of 16 days. For cover all the cycles and all the phases of the cycle of solar cycle. We want to include all the satellites and all the classes of flares to understand if this index trigger also in small flares or only in large flares. And what happened with this index in quiet zone. Well, we use this function in order to calculate a temperature and emission measure from some pi. This function assumes like all the full disk of the sun is like isothermal plasma with a optically clean emission, and until now we use coronal abundances, but we have also the temperature and emission measure calculated with photospheric abundances in order to compare in the next month, I think, these two methods, because Hugh only used coronal abundances. So the temperature is function of this ratio of all the two channels of the clocks, and the emission measure is the function of temperature. So this is an approximation that White used in his paper to explain more or less how this function calculates temperature and emission measure. So we have this ratio of short long band flux, and then we can calculate with this equation the temperature. And with here is the relation between temperature and this ratio of the flux. And with this temperature, we can calculate the emission measure. All these parameters have to be calculated for these two methods, coronal abundances or photospheric abundances. So that is what the function do in SumPy, and how we calculated the emission measure and temperature for all the days. So we use until now the same parameters that Hugh used, and we have now the whole code to change these parameters and to understand if the index is sensitive to these parameters or not. For now, we choose an anticipation window to look if there is a FAI associated to flares, and to look if every FAI alert is associated to one flare. So this is the logic for this index, and we have here an example how it looks. We have this blue lines, that is the peak of the flares. The green line is the start of the flare, and the yellow line is the end of the flare, and the red vertical lines is the FAI. So we can see here in this flare, for example, that we have four triggers of the FAI just before the peak, but we don't have alerts before the start of the solar flare. We want to calculate and see how we can anticipate the peak of the flare, if we can anticipate the start of the flare. In this other flare, that is less class B3, we don't found trigger or alerts of this FAI. This is with this window. So we look 30 minutes before the peak if there is at least one of these red lines. Oh, sorry. Well, and then we calculate the true positive, false positive, and false negative data of all in these years, and the mean of the anticipation time. And we are looking for or study some specific flares to understand what happened in this. For example, here we have an overlapping flares, because we have two flares very close, and we don't know for example, if this trigger is associated to this peak or to this peak for which solar flare. So we adjust this window that we set for looking the FAI alerts, and what it do is it looks 30 minutes before the peak, but if he find another end of the other flare, it stop here, because we think that these FAI alerts are associated to this peak, no to this. So we adjust this window. So now the code do this automatically, and we can change the other threshold to find if there is a FAI alerts. We can see how many FAI alerts we have until the start of the flare, until the peak of the flare, or until the end of the flare, or between the peak and the end, or between the start and the peak. All the possibilities the code can calculate to understand what happened. So we can do a lot of statistics with this data. And this is the same. For example, if we have no overlapping flares, we use the time of the peak minus 30 minutes. If we have the overlap, we use the time of the previous end flare, and we can adjust this time. Well, so we can change a lot of parameters, and for now we only change this window, and we are almost ready to play with these other parameters. So here we reproduce the graphics of the paper of Hugh, and we talk with him in order to understand if the method is running correctly. And now we have the check of Hugh, so we know that the code is running well. So we can expand the statistics. For this first approximation, we use 200 days, and we find in these days 1,000 of flares that was analyzed. And here we have these graphics when we can see how many flares are or have associated FAI alert, and how many doesn't have. So in this plot, we can see that almost 84% of the flares in these 200 days have a FAI associated to these flares, and we have a little part of these days that these flares don't have alerts. So we want to see what happened in this, but we have now a good approximation about anticipation or alert. But the problem is here, when we try to understand if the FAI's alerts, if all the FAI alerts are associated with at least one flare, we found that we have a lot of FAI alerts that don't have a flare associated. So these FAI alerts are the false positive rate. So we have 57% of false positive rate. And in these 200 days, we find that we have the average of the anticipation time between 25 to 30 minutes. So this is the statistics until now. We have a good detection rate, but we have a false alarm rate that is not the best. Well, this is the same statistics. So what we think to do next, or what we do next, we did next is expand the here we classify by class of the flare. So we have here the percentage of flares with at least 1 FAI before in these 200 of days. So for example, here we see that we have a few flares of class A, but these flares don't have these FAI alerts. But the larger flares, well, here we have only one, but the 100% have FAI alert just before. And here we have an example. This is a M2 class flare with all these triggers. And here we see that the earliest FAI alert remains 3 minutes in this trigger. And this is the false alarms. We don't have good statistics here. We have a lot of FAIs that are not associated to solar flares. And for example, we see here that there is a few FAI alerts. We want to study some of these solar flares specifically to understand what happened here, but here we have this anticipation time of 29 minutes. That is very good, I think. And we do these graphics of correlation. This is the flux versus emission measure and the flux versus temperature. And we see that there is a correlation here. And we use these colors by class of the flare, and we can see that maybe there is a groups here. And if we expand the days to 1000 days, we see the same correlation, but we find another line here and this vertical line data. And this is the emission measure calculated in the start time of the flares. And we find a bigger line here. So we have to clean the data for these error values that we can see here in red. That we think that is because we subtract the background, just switch the data 5 minutes and then subtract the shift data between the original data, and we find negative values of flux and some values, small values of flux. So we think that maybe this is happen when we calculate with the function of some pi, that we have this data then don't correspond to the real values. Here, if we do this zoom in this graph, here is the temperature and here is the ratio of the channels. Is the same graph of here, but with this zooming. And we find that this is error values. So we filter these values, we filter negative values and non-values. And with this data cleaning, we have a few data that can be analyzed to, or can be an FAI alert of the solar flares. Also, we explore in these 1,200 days how many solar flares we have. So we have almost 7,000 flares, but we have a few flares, large flares, and we have a lot of these class flares. So in the future we want to analyze the same number of flares of every class. And here we have the minutes to the peak and to the start to the time to the start to from the start to peak, from start to end, and from peak to end of the solar flares. Just for try to understand if we can expand or increase the window for look these FAI alerts. So with this data expand, we find almost the same percentage of the flares with associated FAIs and of the FAI that have associated are associated with flares. So the statistics show that don't change if we increase the data. So we have the same. We have a high detection of these FAIs, but we have high false alarms. So we don't know until now how we can do this smaller. And we plot here the anticipation time that we found in this 1,000 of data. So this is the time, the anticipation time to the start, the anticipation time to the peak, and this is the time to the sign to the another flare, because we want to see if we have 2 or 3 flares very close. So we found that we can anticipate almost 30 minutes to the peak with this FAI. That is a good time. Here is the same graph by class, but with this expand data. And we see here that we have, for example, for this larger class flare, 26 flares, but we have a few of these flares that don't have a FAI alert. So we are wondering if this FAI works for larger flares or don't. Here is a good example. We can see that the FAI triggers every minute to say that there will be this flare, M class. But here we have another flare also of M class, but we don't have a trigger. Here there is only one. So we want to understand what happened here. What happened we will have when we have a overlapping of flares. 1, 2, 3, 4 in the solar disk at the same time. And for this flare, the FAI alert works good because we have 30 minutes of this anticipating time. We see that we have the same correlation between the flux and the emission measure, and this is more scattered, but it seems that have the same groups by class. And this is the same graphs, but at the start time of the flare and at the end time of the flare. And we still see that there is a correlation here. And this is how this graph changed if we change the window. This is the full window until the peak. This is the start, from the start to the peak, and the peak to the end. So we have alerts after the peak of the flare, the alert of flares. So we want to understand if FAI trigger not only in this pre-phase of the flares, but in all the phases. And here we have the same graph changing the window. And well, we changed the temporal window because we do all these statistics that I showed before with this time of the window, 30 minutes. But we want to explore only for now if this FAI is sensitive to this window. So we explore a window from 30 minutes to 120 minutes with a step size of 5 minutes. So we have these videos to show what happened, and maybe it works. And we see that we find less FAI alerts that are not associated to solar flares. But we were thinking if it's possible that we can anticipate a flare with 100 of minutes or something like that. So this is just for try to understand what happened. And this is the same, but by class. What happened with these FAI alerts? So we see that the FAI is very sensitive to this window, as we Okay. And here is the flares with have associated FAIs, FLARES, alerts. And we see that it doesn't change a lot. So the problem with this window is the false positives. This is changing the window, the threshold of the window. And this is the alerts before. Well, it's the same video, but changing the threshold of the window. So one, this is for the just until the flare start, and here and until the peak of the flare. So the graph change a little. Yeah. If we increase the window, we can find more fire alerts for just until or just before the start of the flare. And this with the peak. With the peak doesn't change. It's the same percentage here, 15. So now we want to play because we have a good detection rate, but we have a bad false alarm rate. And we want to play now with these parameters, changing the temperature threshold and the emission measure threshold, and the time or the FAI is trigger, for example, 3 minutes consecutive, and or we can change this parameter too. And we want to study these specific cases when we have overlapping events, and try to analyze what happened with these FAI that doesn't have or are not associated with FAIs. So for my master thesis, because it's my work for my master that I have to finish this year, we want to change these parameters and study some of these overlapping events and try to understand the theory of all these physics of this phase of the flare, this pre-phase, and maybe in the future we want to adapt this to machine learning, because if there is a physics parameters that we can measure, maybe we can do some work in this. We are in this moment downloading a lot of data all the days between 1980 to October of this year. So With these all the complete days, we want to do the same study, but maybe in the future, because I think for now I don't have the time to analyze all these days, but it's in our mind that we want to do in the future this. So well, we think that the FAI establishes a thermal precursors as a reliable fair indicators, but we need to optimize these parameters to have good alerts and a good times for anticipation for flares. And we think that the subtraction of the background, because when we calculate the temperature and emission measure, we have only one value for the full disk. So there is a lot of events and things that are happening in the full disk that can affect. So we don't have only the information of the flares, but the old physical things that occur in the full disk in the sun. And this is work for potential users as FOXy mission, because my co-director is working in this mission too, and they need to use a lot of these methods to anticipate solar flares, because these missions focusing on observe solar flares, large solar flares. So for now, we have a high detection rate, but we have a lot of false positives. And we are working in this, and we were happy if you have some recommendations or ideas in order to understand what happened in this topic. And we are I'm working with the Observatorio Astronómico Nacional in Colombia, and with the Group of Solar Astrophysics in the Observatorio Nacional. My director is Santiago Vargas, and my co-director is Juan Camilo Buitrago. We were talking with Hudson to understand the methodology, all the methodology of this work. And for now, I'm here in this exchange with the dinosaur group, also working with Astrid Veronic, that is a professor here in the University of Graz, and he's also give me some ideas to finish my work. And thank you very much for the invitation. Here are some of the references that I used, and that's all. Thank you for listening and for the opportunity.
Thank you very much, Paula, for a very nice presentation. Very important to predict solar flares. And now I'm opening for everyone to have any question. Please, Paulo, go ahead.
Hi, Paula. Thank you for your talk. Congratulations on a lot of work. Apparently, you did. For a master's, that's not a small amount of data to process. So, congratulations on that. I do have a few questions. Maybe you already answered in your talk. Maybe I missed. If that's the case, I apologize. But one thing is for the 200 days, about specific on some questions here. On the pilot, on the 200 days experiment, it was sampling through the different goals years, let's say, satellites.
Yes.
Yes, right from the, sorry.
In 1000. We choose from 1980
Mhm.
to now
Yep.
200 days with the same step, with the
Okay,
same
I see. So
for
it's,
more or less randomly data.
yeah, so somewhat uniform across different, essentially data sets, because that's my question here, because of course the ghost data from the 90s is very different from the current goals are series, right? In terms of the sampling rates, in terms of the noise, and many other things. So I wonder, maybe you discussed this with Hugh and Astrid already, but I'm wondering if it's how the statistics change if you look at just the current data sets. I know the sampling will be smaller because, well, there are less flares or active days, let's say. But I'm wondering how much the characteristics of the data might affect the results. See what I mean?
So if we do the same statistics only with, for example, GOES 18 or something like that?
Yeah, yeah.
Okay.
From the, yeah, I think 16 is the first one of the R series. Like with the
Yeah.
more or less the same kind of the same cadence, same noise properties, things like that. I'm wondering, I'm thinking aloud here, could the different data properties affect the results somehow? Because what I'm thinking is from now on, the FAI would be useful for real-time flare prediction, essentially, right? So, of course, we can test with the old data, but what matters is the new data. So, yeah,
Mm,
I'll shut up. I'll let you speak.
yes, I have upload, but I don't know where. uh, with the for maybe with colors by Observatory, but every goes that. And we don't see a lot of or some correlation or something like that. But we are not uh, we we didn't do the statistics only with one satellite until now. But it's a good idea. I can uh, with because I have now in the server of the University of Graz the some years full years of data. I have a 2025 and 2024, so I can run this with only this data these years to find if there is something different. Mm, maybe I can find, but I don't know where.
No, don't worry if you don't have the, it's just again, like I said, it's just an idea. Maybe because if you already did something or thinking about it, or it might be worth to check. If not now, at some point in the near future, because it might change. Because my main comments, of course, you realize this as well, is the amount of false positives, right? You have lots of true positives, lots of false positives. Essentially, FAI is triggering at anything, right? So sometimes you have a flare, you get it right. Sometimes you don't have a flare, and then you get it wrong. So I agree that it's tuning parameters, right? How to adjust that. So and then I'm wondering if how much that is by the quality of the data, let's say, from different goal satellites. So that's just the idea. Okay.
Thank you for the idea.
Yeah.
Maybe
Thank you.
in
Oh, sorry. Now, out of everything, curiosity, is Milo back in Colombia or still in Berkeley? Do you know?
Milo, are you in Colombia now?
Yeah, Can I speak?
Oh, Milo's here. Oh.
Hey, Paula. So good to hear you.
It's
So,
been a long time. We should chat. Okay.
oh yeah, totally. No, I'm physically in Colombia, but because I'm doing visa stuff, but
Yeah,
I'm still 100% affiliated to Berkeley.
exactly. Okay. Okay. Oh man, good to speak to you. It's been years, many years.
Oh yeah.
Yeah.
Can I complement the answer that Paula gave you just a minute ago? Because that's a really good suggestion, and we have tried to look at that slightly. So Paula already said she made all the same plots that you saw. Example of the XRB versus the emission measure or versus the temperature, but she color coded every single point with its date, just to see if there was some correlation, any parameter, any feature that we can catch in those plots, say like a clustering of some events in certain parts of the plot. We didn't see anything. She also color coded, made the same plot, but color coding by GOES satellite, and we didn't see anything obvious. But it's true that it's worth exploring more, especially because of what you just said. The noise and the sensitivity of each instrument is different. So we can explore a little more of that. But yeah, just so it's a lot of work. I'm impressed with what Paula has done so far. And we are just trying to close it up and make sure that Paula can graduate on time.
There's enough work there already, so write it up. Thank you, Paul. Thank you, Milo. I'll shut up now.
Okay, Gigi have a question too.
Hi, can you hear me?
Yes.
Oh, okay. Nice to meet you, Paula. And I also, nice to meet our Colombian colleagues. And also our Argentinian colleagues. Mariana is here around. And it's nice to see that our talks are now South American talks. It's not only us here in Brazil that talk to us. So very nice talk, very nice subject to study. And following Paulo's reasoning, I want to add a little bit more complexity in your ideas, Paulo, because there is not only the satellite that is changing, maybe the sun is changing, the solar cycles are different, and maybe this FIA, I don't know, shall we say FAI, FIA? I don't know how Hugh
Hugh
says.
says FI.
FAI, okay.
Yeah.
So FAI maybe it's changing from one solar cycle to the other one. And since GOES satellites are almost with the cycles going on, if we do this separation, maybe we will separate also in solar cycles. Maybe a way to uncouple these ideas is introduce some noise in the current data to make it comparable to old data from the 80s. I don't know, it's just an idea. I don't know how to reduce the sensitivity of the new GOES satellites. But there is another point. Is it possible that the false positives are maybe produced because of the average time you take for the data? I mean, if I understood well, you use always 1 minute integration time for the data. Maybe this is too sensitive. Maybe if you increase the average time to 3 minutes or 5 minutes, the false positives will be reduced. I don't know, just ideas.
Okay, thank you. Thank you for the the first idea. We were thinking about the solar cycle. And for that, we are downloading all the data for all the days for see if something happened. But we don't know. Maybe in the future we can do this statistics with every solar cycle. Because we want to know what happened in the quiet zone.
Yep.
For the average, I don't know.
Okay.
Maybe we can change this resolution.
Yep.
But for now, we use the same that Hugh used, because we want first to reproduce the same that Hugh did for understand if we are doing well this work. But maybe we now have all the data 1 minute by minute, so maybe we can do some average.
Okay, just ideas. Not to
Yes,
do it right now. Thank you again.
Thank you very much.
Okay, any other question to Paula?
I have one
I have one also.
because I don't know how to put the hand in Zoom. Sorry.
Okay, go ahead.
Okay, Paula, thank you for the presentation. For me, it was very important because I'm not a specialist in this area. But
Excuse me,
now I
Maria, can you
understood.
talk loud?
Sorry?
I don't hear you very well.
Oh, what happened?
Can you hear me?
We can
Yes.
hear you, but the volume is really, really low.
Oh, really low.
Yeah.
It's good
It's
now.
good.
Now
Yeah,
it's good.
good, yeah.
Okay. My question is, okay, thank you, Paula, for the presentation. It was very explicative. So for me, it's important because I'm not a specialist in this topic. But I don't know if you can return to the page 8. Because, okay, I understood that the idea is that you want to, from the soft X-ray, you want to predict when a flare will occur. But if you see the symmetric microwave or metric radio, you see these oscillations in the emission. I understood that the idea is now to see what happened with soft X-ray. But if you combine with another wavelength, you can avoid this false positive but I'm not sure if every flare have the same feature in the whole wavelength spectrum. But I don't know if maybe this could be a good idea for a future work.
Yes, we can combine with this EUV, because we see the same increase here. And maybe for the future, it's a good idea to compare with some instruments in order to look if we find the same in different instruments. I really like this topic. Maybe in the future I can continue to work in this, and all the ideas will be welcome. Thank you.
Thank you, Paula.
Okay, Jean-Pierre, I have a question too.
Thanks, Paula, for the talk. If I understand well, your FAI works better for larger flare than it works for smaller flare, right?
And this is what we want to prove. But until now, we don't have good results in this. Only for the smaller flares, we don't have a FAI. But for the large flares, we have some large flares that don't have FAI.
Okay, so So I mean, I misunderstood. I thought that it was working better for larger flare than it works for smaller flare. And I was wondering why. But if not, no problem.
You said that if we change this parameter of the emission measure, we can maybe find if the flare that we are anticipating is larger or smaller. But until now, we don't find a lot of these in the correlation. We see that the emission measure is the emission measure, yeah, is greater for the larger flares. But at the time to analyze the statistics, if we have a FAI for every large flare, we see that we don't have.
Okay.
So we are trying to understand what happened there.
Mm-hmm. Okay. Yeah.
Yes, thank you.
Yes, Paulo.
Just last one, because they're discussing the other wavelengths. Another suggestion, maybe again, Hugh mentioned this, at least from the 2010 to 2014, you have the SDO Eve wave bands, right? They're similar to AIA bands, so maybe there's something there that's easy to test, at least for a short period, and see if that helps. Because if you can show that adding another wavelength, especially the UV, that might be something to think about future instrumentation and having that UV photometry tied to soft X-rays to have that ongoing and have maybe help with these prediction flares. Okay, so just throwing out there the idea, Paul.
Thank you, thank you. Yes, we can look if we can have this data and do the same in statistics and compare. It's a good idea to, at least for one or two, I think, flares to.
Yes. Yes, some test cases, see if it works. You won't have the temperature emission measure thing, but maybe there's something that just increase of flux or something to. It's another check, right? It's just, oh, emission measure temperature, good, but then you have other fluxes as a kind of a balance to check.
Exactly.
Yeah.
Yes.
Okay, any more questions?
I actually have one question. Hi, Paula. Thank you for the nice talk. I actually wanted to ask if I think from what you have said on slide 28, you have used the same parameters for all the flares. So, like, what if we divide the flares into two, like impulsive flares and gradual flares? And then I think the parameters will change for both of them, I guess. And then maybe you can make a comparison between both. That can be, I think that can be another idea.
Excuse me, can you repeat the idea?
Like, I think from what you have said, you have used all like same parameters for all the flares, right?
Yes, yes. Yes.
So I think maybe like the parameters can change for impulsive flares and gradual flares. So you can like make a comparison between both of them by changing the parameters for these two types of flares, impulsive and gradual, and make an analysis. That's another idea, just an idea.
Yes, I have also the idea for do the analysis only for every class of flares. Also, we were thinking about what happens if the flare is yes, larger or not. I think we can do that because I can filter only the by class and run the same.
Right.
Yeah, this is a good idea. Thank you.
I have more questions, Paula. Okay, Paula, thank you very much for accept our invitation, and Mariana to the recommendation. And
thank you very much to all. It's nice to meet you all, and thank you very much. I don't know how to run my video.
all right, and good luck for your research and there and in Austria too, and your master degree.
Thank you very much. Yeah.
All right, thank
Yes,
you, everyone.
Thank you, Paula, for the talk. Thank you, everyone, for organizing. See you next time. Milo, we should chat.
Thank you, Paula. Thanks so much.
Let's chat for sure. See you next time. Thank you for the invitation. Bye now.